the systematic stuff. So last class, we started off by looking at another example of computing the required sample size to bound an SRS estimate by a certain amount. Following that, we started to discuss systematic sampling. Systematic sampling is very similar to simple random sampling in that they use the same estimates for the mean and the variance of the mean. And those are given in equation 2 on slide 52. What we began to discuss after that was what we can expect or how we can expect this estimate for the variance of mu to behave compared to the true variance of mu for an actual systematic sample. So the true variance for an estimate of the population mean is given in for the estimate of a population mean when using systematic sampling is given in equation 3. You can see that this estimate is a function of rho, which measures the correlation between pairs of elements within the sample. So it's a measurement that's it's a correlation measurement that determines how similar two values are or two observations are within the sample that we have collected. When we compare the variance of the mean or the estimator for the variance of the mean from simple random sampling to the estimate of the variance of the mean, to the estimator of the variance of the mean for systematic sampling, we can show or we can expect the two estimators to be or to return similar results when rho is close to 0. When rho is close to 1, we would expect the systematic sampling estimator to be greater than the SRS estimator. And when rho is negative, we would expect the opposite effect. So the systematic sampling variation estimator is less than the SRS estimator. So if we are always using the simple random sample estimator for the variance of the mean, if rho is close to 1, it would act as a lower bound, so it will be less than the true variance. If rho is close to 0, they should be approximately equal, so that's the ideal situation. And when rho is negative, it should be larger than the systematic sampling estimator. Period. Okay. All right, so we started to look at we finished off looking at 3 examples or at 3 illustrations of the type of structure you would expect to see in a population that would lead to each of these 3 cases. So, for example, we considered the random population. The random population would be the population structure that leads to a rho that is approximately 0. Then we also considered the ordered population. This is the structure we would expect that would cause rho to be negative. And then we started to consider and left off looking at the periodic structure, which would be the structure that we would expect to generate a positive rho, but that really depends on the value of K for the systematic sample. All right. So on slide 55, we looked at different illustrations to try and emphasize this point. So in the first row of plots for the random population, let's move this down so it's a little more centered. So this way and this way. Okay, so for the first row of plots, we have what would be the random population. So this is basically the independent, uncorrelated population. The measurements do not appear to have any trend, whether it be positive, negative, or curved, or any sort of, there's no sort of apparent relationship here. So this would be the type of population that if we sampled from using a systematic sample, we would expect our estimate of the variance, our estimator for the variance from SRS to be close to the true estimator for the variance of the systematic sample. In the second case, we have what was supposed to illustrate the ordered population. So there are 2 different directions that we considered here, but the result is the same. So in blue, we have an upward or a positive order, and in green, we would have sort of the negative trend or a downward order. So here, in both cases, the idea is when we collect a systematic sample, what will naturally happen as we progress through the observations is we're going to get values that are spread further and further apart. Okay, and this is due to the fact that we have this apparent order in the population. So this is an illustration where we would expect rho to be negative because the observations are becoming more and more spaced out as we pull them into the sample. In the last set, we have the periodic situation. Now, in this particular illustration, due to just the spacing issue and like how I drew the curve, it's not quite as clear what or why the values of rho would be positive here, but I'll try and explain the idea again, just so that we have an idea of what I'm getting at. And then I'll give another example using another illustrative example to try and emphasize this point. So in this situation, we have a population that has what we could describe as kind of like a sine curve style trend to it, right? So we have this fluctuation or consistent fluctuation in measurements for all the observations that are sampled. If we use a systematic sample, we could observe rho being positive if we sample such that we always hit the same point on that periodic trend. So in red, I've only sampled 2 points here, but the red illustration is showing that we are sampling from the tops of the curve. So from the peaks of the sine curve, or from the peaks of the curve. It might not be a sine curve, but now, so in this case, what we would expect to happen is the values in the systematic sample that we collect, because we're always hitting the top of the curve, are going to be very similar to each other. So this would indicate a positive rho. Now this could happen in other ways as well. Suppose that we sampled from the bottoms of the curve. So I'll use these little blue lines here to represent the bottom of the period. Okay, so that would mean that our sample in that case would be these 3 values, but the general idea is the same. These are 3 values that are very similar, and therefore we would expect rho to be positive because the measurements are so similar. And this is just because of where we're hitting the curve. And you could do this in other areas. It doesn't necessarily have to be peaks and valleys, but say you always hit the curve here, for example. Okay, well then you would expect points of this value, but again, very similar. So the periodic population is a population that if we choose K if we sample from a periodic population using a certain value of K, where K is the period in which we collect the value, or the jump between values, we could end up with rhos that are positive because we're always hitting the same part of this periodic curve. Okay, so we can get around this, and I'll give an illustration of how to do that in a moment, but as you might be able to imagine, the way to get around this would be to change your value of K in the systematic sample so you're not hitting at the same part of the curve every time you pick out a value. Okay, so those are the 3 illustrations. So these are 3 illustrations of what we could expect from a systematic sample if taken from populations with these structures. Does anyone have any questions about that? All right, so a few summarizing ideas here based off of the 3 population illustrations that we just looked at. Okay, so the first thing, again, for random populations, we would expect the estimates, or we would expect systematic sampling to behave like simple random sampling, at least in terms of the estimators. So when we're using the estimator for the variance in particular of the mean, we would expect the values returned from the SRS estimator to be very similar to the values returned from the systematic sampling estimator. When we use ordered populations, we would expect rho to be negative. Therefore, the systematic sampling variance estimator should be smaller than that given by SRS. So in this case, SRS would act as a upper bound on the true variance of the mean in this case. Okay. So this should be U hat SY. Right. So for a periodic population, we could observe the opposite effect. So if we are sampling from a periodic population using systematic sampling, we could run into the situation where we underestimate, make sure I get that correct, where we underestimate the true variance if we are using the SRS estimator for the variance of the mean. So much, the lingo, so confusing. Okay, so to illustrate this idea, so again, I guess like key points with the periodic population, that depending on the value of K that you choose for the systematic sample, if you choose the value of K such that you're always hitting the same point on that periodic curve, then you would expect a positive rho. And if you have a positive rho, the SRS estimator is going to act as a lower bound because the true variance estimator is going to be larger than that of SRS because of the rho factor in equation number 3. Okay, so for example, suppose we are sampling from a grocery store, and you can imagine if you think about, like, say you're measuring sales from the grocery store, you would expect to see some sort of periodic trend in sales from a grocery store because most people grocery shop on the same day of the week, and most people as a whole or as a population tend to grocery shop on the same day of the week as each other because of the working schedule that we're all a part of in Western culture anyways. So, well, I guess it's still true even though we don't work from an office anymore. But so in this case, the value of K is going to be very important because you can imagine, given that from Monday to Sunday, you would expect to see some sort of periodic trend in the sales from the grocery store, probably with them peaking on the weekend and being much smaller earlier in the week. The value of K is going to be very important because if you choose K to be, for example, 7, given there are 7 days in the week, you're always going to be sampling on the same day of the week. So if you always sample on the same day of the week, you can expect rho to be positive because the sales on each day of the week are probably going to be very similar to each other. Furthermore, if you sample on the same day of the week and say you choose a day that's earlier in the week, like Monday, Tuesday, or Wednesday, you might actually run the risk of underestimating not only the variance of the mean, but also the true value of the mean. Because if the true value of the mean is the average across all days of the week and you only take values early in the week, you're probably going to miss the days with larger sales. Whereas if you choose a 7-day sampling period, but you always sample later in the week, say Friday or Saturday, then in that situation, you're probably going to overestimate the true mean while still underestimating the variance of the true mean because you still have that positive rho factor that's not being accounted for. So to get around this, if we know that there's a periodic trend present in the population, the simple strategy is to choose a value of K such that we don't hit the same day every week, which sounds really simple, right? So for example, you could sample every 9th day. This is the illustration I gave on the slide. But theoretically, if you have the ability to, you could also sample like every 4th day, every 3rd day for argument's sake. And this would allow you to hit different points along the trend and give you a better representation of the data. And it would, as a result, create more of a random sample, though you would still see the periodic trend. So you would still expect there to be some positive correlation between the values, because even if you hit every 3rd day or 9th day, you would still see the values kind of bounce around with the curve. But the estimate for the mean itself should be closer to the truth because you are hitting highs and lows in sales. But the variance for the estimator of the mean will probably still act as a lower bound on the true variance because you would still expect there to be some positive correlation between those values. All right. All right. Does anyone have any questions about the systematic sampling information? Okay. Have you guys been watching the GameStop ticker go crazy over the last few days? It's been, I have some friends that got in on it. It's been very stressful in the group chat. Yeah, it is. And now there's a bunch to watch because there's AMC, Nokia. There is a rumor that Blockbuster was coming back. That one was pretty funny. They're like 11 cents a share or something. But yeah, it's insane is a good word to describe what's going on for sure. Okay, so we're going to work through some examples now, all related to the systematic sampling scheme. So we have some preliminary, like basic examples just about bounding estimates, creating confidence intervals, things that we have seen before for the SRS situation, but just in a slightly different context because we're working with systematic samples. We'll talk about proportion estimation, maximizing a proportion, sample size calculation. And then we're going to talk about repeated systematic sampling, which is where you conduct systematic samples kind of within systematic samples. And that's a cool idea because you can create ANOVA tables and you can use it to estimate rho. So I actually really like that, that part of the material quite a bit. I think it's really neat. And actually, in general, I like the systematic sampling stuff the most. This was always the sampling scheme I thought was most, I don't know, out of all of them, this was the one that I liked the best for whatever reason. Maybe it's just more intuitive than the other ones, but anyways, so we'll start with some preliminary examples. We'll talk about things that are slightly more interesting afterward, but just as a basic starting point, so we have here, a college is concerned about improving its relations with the neighboring community. A 1 in 50 systematic sample of the population of size 4,500 students is taken to estimate the total amount of money spent on clothing during 1 quarter of the school year. What is little n? Compute the estimate for the total if we have the sum across all observations in the sample of 850, and then place a bound on the error if we have an estimate of sigma hat. Okay, so we have capital N is 4,500. We have a 1 in 150 systematic sample. So that means that K is equal to 150. Maybe I'll just move this part up here. So we know that K is equal to capital N over little n. So therefore, K is equal to, or little n is equal to capital N over K. So that's 4,500 over 150, which is 30. All right, in part B, we want to estimate tau. We want to estimate the total amount of money spent on clothing during 1 quarter. So we want to estimate tau for this particular experiment. So tau hat SY is equal to capital N multiplied by mu hat SY. So this is the same relationship that we had established earlier with simple random sampling as well, just that the total is equal, the estimate for the total is the estimate for the mean multiplied by population size. So this is going to be 4,500 multiplied by the sum I and S yi over little n. So this is going to be 4,500 multiplied by 850 over 30, which is equal to $127,500. Right. And then the last thing we want to do is bound our estimate for the total. Okay, so the bound is going to be capital N multiplied by the square root, or I guess here I'll write it out a little bit more formally. So is going to be the variance of tau hat sy. Okay, so this is going to be the square root of n squared. Sorry, and I also forgot one thing. So this will be 1.96 multiplied by 4,500 multiplied by the square root of, oh wait, so we have to check this thing. 1 minus little n over capital N is equal to, should be very small, right? 3 over 450. Yeah, it's gonna be tiny. 1 and 150. Yeah, okay. So we can ignore the FPC here. Sorry about that. So we don't need this part. Okay, and then we'll have 18.40227 squared divided by 30, which is equal to 29,633.25. Okay, so that's our first illustration. Again, pretty basic illustration. This is just kind of find an estimate, bound the estimate, typical sampling question. Kind of neat because we didn't have to use the FPC here, so it's nice to see an example without that. But otherwise, I don't think there's too many tricks. Just remembering the notation for the systematic sample. So we have a 1 in K systematic sample. That's why K is 150. Does anyone have any questions about that? Okay, so we're going to use the same information in the next question. In this question, we're asked, what is the sample size required to estimate tau within $10,000? Okay, so as a reminder here, we're in a really nice situation. Well, Okay, so sorry, what I meant to say is we're going to use the same information, right? So we have sigma hat is equal to 18.40227. And then we have capital N is equal to 4,500. All right, so, oh, and then we want our bound to be 10,000. Yeah. There we go. Okay, so we're going to have B is equal to the square root n squared multiplied by the variance of tau hat sy, or sorry, n squared multiplied by, so this would just be, sorry, variance tau hat sy, that's going to be n squared. Okay, so this will be the square root n squared 1 minus little n over capital N, sigma hat squared over little n. Okay, now what we have to do is rearrange and solve for n. So we've actually seen an illustration of how to do this already. So we looked at in full the solution for little n given a finite population correction for SRS in the context of the mean. So following the same strategy, we can show that the estimate for little n in this case is going to be b squared divided by 1.96 squared multiplied by sigma hat squared n squared plus 1 over n inverse. Okay, and then I'll just make a note here. So you're going to compare to slide, and then we would be comparing this to slide 41. And you'll notice that the only difference here is just the n squared, how the n squared factor is being used. Okay, so as a reminder, we can ignore the 1 over n factor when n is very large. But the problem is that capital N being very large depends on the problem we're working with. So it really depends on our estimate of the variance or the estimate of the standard deviation, the bound, or n the bound. So we have capital N here, so we'll include it in the calculation, but we can check to see the difference very easily. So this is now going to be 10,000 squared divided by 1.96 squared, 18.40227 squared, multiplied by 4,500 squared, plus 1 over 4,500 inverse. Okay. And this should give us 248.8697. Okay, so that's the first part. The question actually asks us for the systematic sampling scheme. So the final answer we're looking for here is the 1 in K systematic sample. So we have little n is 248.8697. So given that result in a sample size calculation, we're always going to round up. So we'll have use n is 249. Right? Because as you'll recall, if you round down, you could miss the actual bound at the confidence level that you're working at. I'm just missing things everywhere here. So now what we would do is we would go K is equal to capital N over little n, which is 4,500 divided by 249. Okay, so this is going to be 18.082. And now what we would do is we would round down to get the sampling period for the systematic sample. So use 1 in 18 systematic sample. So similar style question, familiar flavor in terms of finding sample size. A nice twist because you have the systematic element to it. So there's a little bit extra there, but for the most part, pretty similar to what we saw in the SRS case. So we've seen 3 examples of sample size calculation now, all pretty familiar, or all pretty much the same. If we were interested just to determine the effect of the 1/45 here, or 1/4500, so that's a pretty small value, but nonetheless, if we took a quick look at it, times 18.40227 squared times 4,500 squared. Okay, and then if we ignored the factor of 1/n, yeah, so it's a pretty big difference. So we can say note, ignoring 1/N gives n equals 263. Basically just to say that 4,500 really isn't large enough in the context of this experiment to justify ignoring the 1/n. But again, it's sort of a subjective problem, or not a subjective problem, but it really does depend on the variation estimate and the bound that we're trying to achieve and the confidence level that we're working with, because the multiplier 1.96 is because of it being a 95% confidence level. But if we were to use a 90% or a 99% confidence level, we would have a different multiplier. Okay, so moving on. Does anyone have any questions about that? So round up for sample size, round down for systematic period. Opposites. Okay. All right, so our proportion estimation schemes work in the same way that they would have in the SRS case. So when we're estimating a proportion, we're considering a binary characteristic as being the value of or the characteristic of interest. So we're basically counting the number of times we observe a certain outcome, dividing that by sample size, and that becomes a proportion of times that we observed a certain outcome. Our estimate for the true proportion of the outcome of interest is going to be the number of times it occurred divided by little n. And the estimate for the variance of the proportion estimator is going to be the finite population correction multiplied by pi hat for the systematic sample times 1 minus pi hat for the systematic sample divided by little n in this case. So slightly different from the SRS one, because I believe we had n minus 1 in the denominator for the SRS estimator. Let's take a quick look to see if that's. Yeah, we did have an n minus 1 there, but for the systematic sample, we're using just over little n, but very similar. Okay, so in a systematic sampling scheme, we'll look at some applications of these formula. So for example, we conducted a 1 in 6 systematic sample to obtain from a voter list the proportion of voters in favor of the proposed bond issue. So we're basically just counting the number of people that are in favor of the issue versus the number of people that would be opposed to the issue. So several different random starting points are used to ensure the results of the sample are not affected by the periodic variation in the population. The coded results of the pre-election survey are shown in the accompanying table. Estimate pi, the proportion of the 5,775 registered voters in favor of the proposed bond issue with a 95% confidence interval. So basically our goal here is to estimate the proportion of people that are in favor of the bond issue. Okay. So we have a sample size of 962, and we have we have a count of the number of people that are in favor of the issue, which would be 652. So we're going to have pi hat sy is just going to be 1 over little n multiplied by the sum for all I and s of yi. This is going to be 1 over 962 multiplied by 652, which is going to be 0.658. All right. Okay, we want to build a 95% CI for this. So the 95% CI will be pi hat sy plus or minus the bound. So the bound here will be 1.96 multiplied by the square root. Oh, and then always have to remember to do this. So we'll have FPC 1 minus little n over capital N. So this is going to be 1 minus 962 divided by 5775. Okay, so that is 0.833. Okay, so we're going to keep the FPC. All right, so our bound will be 1.96 multiplied by the variance of pi hat sy. So this will be 1.96 multiplied by the square root of 1 minus little n over capital N, pi hat sy, 1 minus pi hat sy divided by little n. This will be 1.96 multiplied by the square root 1 minus 962 over 5,775 multiplied by 0.658 times 1 minus 0.658 over 962. And that should give us 0.02697. Therefore, the 95% CI is 0.658 plus or minus 0.02697, which gives us 0.631 to 0.685. So we are 95% confident that the proportion of registered voters in this county that are in favor of the proposed bond issue is between 0.631 and 0.685. And then actually just in reading that sentence over, we could also, probably be a little bit more, we could probably take the time to write the sentence such that it's more communicable. We could communicate it better to the layman. So we could say, instead of the proportion of voters in the county is between 0.631 and 0.685, we could say, we're 95% confident that between 63.1% and 68.5% of registered voters in the county are in favor of the proposed bond issue. I think that would make more sense to someone that doesn't have the background. But both statements are technically correct, but one statement would be more generalized, I think, than the other. All right. Okay, so let's look at a sample size problem, a sample size calculation problem in the context of proportion estimation. Okay, so we have here an advertising firm wants to, sorry, 1 second, I need to get. Okay, so an advertising firm is starting a promotional campaign for a new product. The firm wants to sample potential customers in a small community to determine customer acceptance. To eliminate some of the costs associated with personal interviews, the investigators decide to run a systematic sample from capital N equals 5,000 names listed in a community registry and collect data via telephone interviews. Determine the sample size required to estimate pi within 3%. Okay, so in this situation, we can make the following notes. So here we have capital N equals 5,000, and we have little b is 0.03. Right? So little b is going to be 1.96. So we're just going to assume 95% significance level, nothing stated. So the standard would be just to assume alpha 0.05. And then this is going to be multiplied by the variance of pi hat. Okay, so then we have 1.96 multiplied by the square root of 1 minus little n over capital N, pi hat sy, 1 minus pi hat sy divided by little n. Okay, so this, via some manipulation, we can show that we'll end up with the following. So b squared over 1.96 squared equals 1 minus little n over capital N, pi hat sy, 1 minus pi hat sy over little n. Actually, yeah, that's fine. Right, and then we can show that this thing turns into b squared divided by 1.96 squared multiplied by pi hat sy, 1 minus pi hat sy, which is equal to 1 over n minus 1 over capital N. All right. So that gives us little n is equal to b squared over 1.96 squared pi hat sy, 1 minus pi hat sy plus 1 over n inverse. Okay, so we have b, we have capital N. What do we do for the pi hat sy? So this is actually a problem that you've probably seen before, but essentially the idea here is there's a value of pi hat sy that we could consider to be optimal, so that, or we could consider to be the most conservative. So it's the value that's going to give us the largest sample size, but that would guarantee that, or that would give us the highest chance of actually obtaining the bound at the confidence level that we're looking at. Whereas the other sample sizes, or for different values of pi hat, we risk underestimating the bound that we are trying to achieve. So to illustrate this idea, here actually I'm going to move this part down here. So I'll write this as so what is pi hat sy in this scenario? Actually, and let's say, instead of like what is, we'll say what is optimal. Okay, so the answer here will be the pi hat sy that maximizes sample size. Okay, so there's a few different ways that we can approach this problem. Now, from like a piece of paper in hand style approach, it's a fairly cumbersome empirical proof because you have to plug in all the different possible pi hats, get the sample sizes out, and then plot them. This is something you can do very fast though. If you have even Microsoft Excel, you can do this in minutes or seconds, I should say. But just to illustrate the idea so that we have a sketch of what we would expect to see. If you consider the following grid, okay, so we just have a regular plane here, we have sample size, and then we have pi hat sy. And then we range the pi hats from say 0.1 to 0.9. All right. So if we were to start plugging in these various values of pi hat, and some of you probably know where this is going, we're going to observe a trend that looks something like this. So I will use a scale of, so if this is 0, we'll go 200, 400, 600, 800, 1,000. Okay, sorry, I'll finish this up quick. So for 0.1 and 0.9, you're going to be about here, which is like 350. For 0.2 and 0.8, you're going to be at 600, which is right about here. For 0.3 and 0.7, you're going to be at 760, which is right about here. For 0.4 and 0.6, you're going to be at 850. And then at 0.5, you're going to be at 880. Okay, so this is optimal. And the point of this exercise is to show that when we are actually doing sample size calculations for a proportion estimate, the optimal sample size calculation will always be found when you consider the pi hats to be equal. So when they're both 0.5. So if we use pi hat equal to 0.5, just I'll just finish this up really quick here. Okay. So use pi hat sy equals 0.5. Then we have n is equal to 0.03 squared divided by 1.96 squared, 0.5, 0.5 plus 1 over 5,757 inverse, and that should be in the area of 879.4228. Okay, so therefore n is equal to 880, and that means that k is equal to 5775 divided by 880. Okay, so that's 6.56. So we're going to use a 1 in 6 systematic sample. All right. Okay, sorry, I was a little rushed at the end there, but got it done. Okay. All right. Okay, so I'll stop there. Sorry, I went a little overtime today. So on Monday, we'll have that quiz during the lecture hour. So again, let me know if you have any questions or concerns or whatnot. The room for the quiz is CCC 9103. It's in the course outline. I sent out an email, but I'll send a reminder. Assignment 2 is due in a few weeks, I think like February 12th or something like this. It's a little whiles away. But the systematic stuff is the first part of it, so you can get started on it if you want. And I think that's it. So as always, if you guys have any questions, please let me know. And otherwise, I'll talk to you on Monday morning at 9.